Hello everyone. I'm Hannah, the project manager of Mending Broken Hearts, and presenting with me today is Ria, the systems co-lead. We're a team from the University of New South Wales from Sydney, Australia, and together we make up 20 undergraduate students from a wide range of engineering backgrounds. In Australia, heart failure accounts for almost 1 in 50 deaths, equating to around 9 people losing their lives each day. However, the solutions in the market for this are very limited and are only temporary replacements for patients as they wait for a donor heart that may never come on time. And so, no matter what solution you choose, the experience of relying on a mechanical support device can be extremely daunting and an unnerving experience for not just the patient, but also the clinicians involved. Thus, this year, we made it our mission to develop a destination TAH that truly centers on the needs of both patients and clinicians, making this life-changing journey as smooth as possible. Thus, we established a set of design requirements to guide our design processes. First, our heart must have the essential functions of a natural heart to ensure sufficient perfusion throughout the body, whilst being durable, biocompatible, and being so that it can function reliably over time without adverse reactions. We also have our non-functional requirements that reflect our mission to be user-centric and also target a lot of our unmet needs in the current TAH market. So for example, our design prioritizes being lightweight, minimizes noise, and has the ability to adapt physiologically. It also offers real-time monitoring to detect, respond to, and record changes in the patient's condition, allowing clinicians and researchers to export data for further research, all while emphasizing data security and protection.
So our design incorporates Hazel actuators, which is a new technology unprecedented in circulatory support, which basically expands when a high voltage is applied and returns to its initial shape when the voltage is removed. These actuators are then used to induce contractions of two soft chambers, which contain the blood. These components are housed in a rigid shell with silicon valves to ensure unidirectional blood flow. We've decided to house each side of the heart in a separate rigid shells, creating a modular design that facilitates easier implantation and adjustable orientation to fit the unique anatomy of each patient. In designing the shape, we focused on maximizing displacement of Hazel actuators while avoiding organ interference and preserving the atria to keep future heart transplants viable. We evaluated the anatomical fit of our designs using Autonomy V patient simulations and plan to seek further input from surgeons at St. Vincent's Hospital to refine implantation procedures. While our current prototypes are 3D printed, our next steps include investigating lightweight, cost-effective, and biocompatible materials that meet clinical safety standards. So currently, our soft chambers are made from silicon, and they are hand-painted inside 3D printed molds. And future work includes investigating surface modifications with PEG or PVAM for improved hemocompatibility before conducting fatigue tests, which is followed by hemocompatibility testing at the Victor Chang Heart Research Institute. In our prototype, silicon umbrella valves are used to ensure unidirectional blood flow, and future work involves collaborating with the valve team at UNSW, who are developing tricuspid valves made from silk. But what really sets us apart is definitely our actuators. These pump the blood without the need for motors or pneumatic drivers. They're made from cheap, accessible materials, and they are lightweight and operate silently. With a higher power density than human muscle, our actuation allows for controlled variable motion for fine-tuned blood dynamics. The actuators themselves consist of a flexible polymer pouch containing an insulating liquid dielectric and a pair of electrodes positioned on opposing sides of the pouch. So when a high voltage is applied, these electrostatic forces draw the electrodes together, which displaces the liquid inside and alters the shape of the pouch. So once the voltage is removed, the dielectric quickly self-heals and the pouch returns to its original shape. In developing the Hazel actuators, we have explored various materials and manufacturing techniques. Our current method uses a modified 3D printer with a copper head to heat seal the BOPP films into circular pouches, which are then filled with distilled water and fitted with carbon electrodes. We have tested different volumes of dielectric and evaluated potential displacement. And additionally, we have conducted heat sealing using a linear actuator to assess durability. By collaborating with Artemis Robotics and using the university's high voltage lab, we have verified Hazel's technology, though it does currently have a limitation of only 8 millimeters displacement. So our current focus is on improving this by replicating 100% plus strain, which has been achieved by others. However, we have not yet observed measurable force or displacement due to air bubbles in the hazel, which definitely limits the voltage to 4 kilovolts to avoid dielectric breakdown. So in order to enhance displacement, we must find a method to remove the bubbles, increase the dielectric permittivity, and use lighter electrodes with more surface area, as well as stack the hazels. Hazel also faces two main challenges. First, it requires DC high voltage, which is incompatible with transcutaneous power transfer mechanisms that do require AC. So future steps may involve integrating an AC to DC converter and a high voltage amplifier within the body. And second of all, high voltage poses, of course, safety concerns, making regulatory approval difficult. So we will have to explore something called HAV actuators, nanotubing, carbon nanotubes for better capacitance and insulation for wires to reduce voltage and ensure biocompatibility. Due to safety concerns, we cannot yet test the Hazel actuators directly in a mock loop. So instead, we have modeled the Hazel actuator motion with a linear actuator in order to assess our device's flow rate and pressures. We have reached initial flow rates of 2.5 liters per minute at 12 millimeters of mercury. However, we were limited by the speed constraints of our linear actuator. From this, we do estimate our hazels will need to operate at 120 BPM or 2 hertz to achieve a flow rate of 5 liters per minute. Our main concern with this is that while hazels only have a roll-off frequency of 120 hertz, a higher frequency will require faster prefill and will also result in an increased risk of damage to the blood cells. Our device focuses on 3 electrical areas, providing controllable input to the hazel, monitoring health of the patient, and relaying data to clinicians and patients via an app. We created a PCB schematic for hazel input with a microcontroller, which manages the voltage regulator and optocouplers, acting as switches for the actuator. This design is compact and ensures the microcontroller from high voltage for safer communication with the app. However, commercial high voltage optocouplers are definitely costly. I think it's around $400 each. So we do plan to manufacture our own to reduce these costs. For patient monitoring, we use force-sensitive resistors to estimate blood pressure and a Hazel extension sensor for actuator control and real-time displacement data. The sensor's capacitance increases with extension, which our microcontroller translates into extension levels, and testing and further development for sensing blood oxygen and flow rate are definitely ongoing. The app, which is designed in Figma, has 2 sections. So one is for patients to monitor battery life, track appointments, and input data, while the other is for clinicians to view health key metrics, such as flow rate, blood pressure, and feedback from St. Vincent's Hospital staff who have worked on other devices such as HeartMate 3 and Vivacor TAH, has guided the app's user-friendly design that seeks to include patients from all age groups and technological literacy. However, Bluetooth compatibility does raise cybersecurity concerns, so future work does include user trials and further app development.
The MBH-TAH aims to initially target the Australian market, leveraging the $50 million government-funded Artificial Heart Frontiers program. This initiative provides opportunities for research, collaboration, media coverage, and technological advancements. Key beachhead Australian target markets include hospitals like St. Vincent's and Prince of Wales, where existing clinician relationships offer credibility and clinical support for our TAH development. After establishing a presence in Australia, we plan to expand into the global market, valued at around 1.87 billion USD. However, regulatory approval is required before market entry, so the primary focus for us is to pass the TGA approval in Australia, which involves Class 3 medical device regulations for the TAH and its accompanying app. So the total cost for just TGA approval for both the app and the heart is estimated at around $140,000. So taking that into account with the estimate costs of bringing our app and TH into the Australian market, we estimate that our TH will cost around $130,000 as a one-time purchase, with ongoing maintenance expenses ranging from 130K plus, depending on the device's lifespan. So now I'll go into our team structure. So our team operates as a hybrid structure under the UNSW Vertically Integrated Projects VIP program for our technical team and the ARC Club system for our non-technical teams. So those unfamiliar with VIP, it's an academic initiative at UNSW, so our university, that allows students to participate in multidisciplinary research projects for credit. So, however, one of the challenges we encountered was accommodating for students who couldn't enroll in VIP, whether they had no elective space left or postgraduate students who were unable to join for credit. So we allowed for extracurricular participation. This way, we retained talented members who might have otherwise been excluded. And this inclusivity has not only strengthened our team, but made MBH accessible to those who are passionate about our mission. On the technical side this year, our team included 3 core sub-teams: mechanical, electrical, and software engineering. However, next year we plan to establish a systems team, which serves as the bridge between these sub-teams. This team will focus on ensuring integration across the hardware and software components, a crucial step as we approach more advanced stages of development. So Ria, who's presenting with me today, is one of our systems co-leads for next year. On our non-technical side of the team, we have these 3 sub-teams that are all under the UNSW ARC Club system. And so this way they can receive recognition for their efforts despite being extracurricular members. So how does MBH actually function? So we have our weekly meetings for the whole general team, and that is the backbone of our team management strategy. We also have separate technical team meetings that allow for focus updates and brainstorming. And back to our general whole team meetings, these meetings also include our academic advisors and our PhD mentors who help give us a lot of feedback as we plan the week ahead. We also have drop-in workshop sessions that are run by our team leads, and this has played a key role in fostering teamwork and cross-disciplinary learning, ensuring that no one is left behind. Our success has stemmed from a few key strategies. Firstly, we've defined a clear goal. So from day one, we aligned every decision with our mission to create a user-centric TAH. And second, we used resources effectively. We maximized UNSW's facilities from makerspaces to mock loops and sought feedback from clinicians and advisors. A key lesson we learned here was not to hesitate in asking for help. Once we reached out to the clinicians at St. Vincent's Hospital, the progress that we made with our app had skyrocketed. And so looking ahead, I'd like to share some advice for some future teams. So first, prioritize organization and communication. Establishing clear structure with defined roles early on really helps to guide people so that everyone knows what the responsibilities are. Leverage mentorship. Your universities will be filled with researchers and experts who are eager to share their knowledge, so it would be good to take advantage of that. Foster inclusivity. Make sure everyone on the team feels valued, as a supportive environment will help you retain talent for future leads and maintain morale. Embrace flexibility. Be prepared to adapt because, for example, this year, our software team was only created halfway through the year to meet the increasing demand in developing our app. And secure funding early. So building relationship with sponsors and university administrators as soon as possible, because some companies set their budgets at specific times of the year. So you have to be very key with your timing when sending your prospectus, as this can increase your chances of success. And lastly, celebrate wins and learn from failures. Recognizing achievements keeps the team motivated, while analyzing setbacks can help you improve. Our experience in the Heart Hackathon has been both challenging and rewarding, and we're really proud of how far we've come. This project was only made possible through the commitment of our sponsors, Abbott Office of Chief Scientist Engineer, and the collaboration of clinicians and research institutions. Thank you.